Everybody to our third talk of the morning session. So I'm pleased to introduce Benjamin Kane from Hong Kong University. Ben's going to be talking about explicit class number formulas for Siegel-Weil averages of ternary quadratic forms. Okay, Ben, take it away.
Okay, thanks. So it seems that every time I want to come to India, something seems to happen to me. I had some visa trouble at one point. This time I broke my collarbone, so sorry I couldn't make it. I would have liked to have been there. So I'm doing my best to, hopefully I prepared some slides that are interesting. I'm able to type now as of a couple days ago, so this is what I could put together. Hopefully it's good. All right, so thanks everyone for the opportunity to speak. Thanks to the organizers. If you have any questions, go ahead and ask, stop me whenever. There we go. Okay, so what is a quadratic form? Well, a quadratic form is a homogeneous polynomial of degree 2. So it has multiple variables, x1 through xn. And you have the degree of every term is 2 in the variables xi, xj. And basically we group these together into what we call classes. So roughly speaking, I want you to think that Q and this calligraphic Q are the same if we can just do a change of variables. So for example, maybe let me just draw here. So a really simple example, and pardon my, so x1 plus x2 squared plus x2 squared is essentially the same as x1 squared plus x2 squared, because I can just do an invertible change of variables over the integers to go from one to the other. So you should think of these two as essentially being the same thing. Is that clear? Okay. All right, so that's what isometry roughly means. And classes are the things that are isometric to each other. So we group them into these groups of isometry classes where we say these are essentially the same quadratic form. And then we count the number of isometries from 1 to itself. So maybe it has some symmetries. The one that I just wrote, x1 squared plus x2 squared, you can flip x1 and x2, and this is an isometry from the thing to itself, from that quadratic form to itself. So it sort of has some self-symmetries. So the number omega sub q is the number of self-symmetries in some sense. Now, we can also, instead of invertible over z, we can have invertible changes of variables over the p-adic integers. So we can think of them as p-adically the same. And this isn't necessarily equivalent, right? So sometimes modulo p squared, and so on, they can be the same, although they're not actually the same over the integers. And the change of variables doesn't have to be the same for every p. I should mention that, because of course, it turns out that it is the same if it's the same for every p simultaneously. Now, we now group together the classes into a genera, which are the ones that are p-adically the same for every prime p. Okay, so if our two quadratic forms look the same, modulo every integer, or p-adically for every prime p, which is equivalent, then we essentially say that locally they're the same. So that's what the genus is. It's the local equivalence. Now, from these quadratic forms, we can form a theta series, which just essentially counts the number of ways that you can write an integer n as using the quadratic form. So rq of n is just the number of ways to write n as q of x equals n. So this is q to the q of x. And then if we group all together all the ones where q of x is equal to n, you get this sum on the right. And this is a modular form, and there are certain techniques that can be used to understand it. For example, if we take the quadratic form that's just the sum of 4 squares, then it turns out that this theta series is in, well, it's basically a 2-dimensional space, but it's spanned by a certain what are called Eisenstein series, and you can prove Lagrange's 4 squares theorem that every integer can be written as the sum of 4 squares because RQ of n is always positive. So this is one way to prove it. Okay. Now, what about binary quadratic forms? Binary quadratic forms means 2 variables, and these are related to class numbers. So a binary quadratic form of discriminant D, we're going to take QD to be the set of all of those. And if we take all the primitive ones, that is the GCD of A and B and C is 1. So ABC is AX1 squared plus BX1x2 plus CX2 squared. Then we can count the number of primitive ones, and the class number of the discriminant D is the number of different primitive quadratic forms of discriminant D. Okay, so this counts the number of equivalence classes modulo equivalence over Z. Okay. And the famous Hurwitz class number formula relates this to the L value, L chi D1, which we'll need later. The Hurwitz class number is a slight modification of the class number where we weight it by 2 over omega q. So basically, for most quadratic forms, for most binary quadratic forms, omega q is actually 1. The number of these sorry, omega q is 2 because you can always replace by multiplying by -1 and multiply everything by -1. But other than that, there usually isn't anything else for most discriminants. And it turns out that omega q, the number of these isometries from the form to itself, for binary quadratic forms, it only depends on the discriminant. And it turns out to be natural to weight things this way. And then we look at what h of absolute value of D is counting. So this one on the left is counting all of the binary quadratic forms, whereas this one, these ones are the primitive ones, right? So this is primitive and this is all, basically. Okay. And so the right-hand side is just counting. So h of D over F squared is the ones that are primitive for D over F squared. And then we multiply everything by F and we have GCD equal to F. And so that's exactly why we get this sum. Okay, so I want to relate these with ternary quadratic forms. And for the sake of simplicity, I'll restrict to diagonal forms, meaning that it's the sum aj xj squared, where the aj's are a vector of length 3. But in general, we can do this for, we can do what we're going to do in this talk for non-diagonal ones. Okay. So the special case where I take just the sum of 3 squares was investigated by Gauss, and Gauss found a formula for the number of ways to write an integer n as a sum of 3 squares. And the interesting thing is that this is closely related to these Hurwitz class numbers. So R1 of n, if n is 1 or 2 mod 4, is just 12 times the Hurwitz class number of 4n. If it's 3 mod 8, it's the Hurwitz class number of n times 24. And if 4 divides n, then we just divide by 4 and keep going. So you can easily check that if you have the number n equal to q1 of x, and n is divisible by 4, then all the variables must be divisible by 2. And so you just divide everything by 4 and then you keep going. So you just keep doing that until it's not divisible by 4 anymore. Okay, so that's just a congruence condition argument. So that's a local condition that says that. And then if n is 7 mod 8, you get 0. Okay. So I defined this theta series before, theta q, and now I'm going to define a kind of weighted average of these theta series. And this is the Siegel-Weil average. So Siegel looked at this, and Weil did some later special cases of it and extended it to different domains. And what we do is we take and we weight theta q by omega q, by 1 over omega q rather. And so it's kind of, remember, this omega q is counting the number of self-symmetries. So we're dividing out by the self-symmetries. So in some sense, these are the truly distinct representations in some sense. And now in this case, because we're looking at more variables, like 3 variables or more, this doesn't just depend on the discriminant anymore. It actually depends on the class, on which class you have. So we sum over the classes in the genus. The genus, remember, was the ones that were locally the same. So modulo every prime power or modulo every integer. And what we get, we call the representations by the genus. And this is what we're going to be interested in this talk. So Siegel showed that the coefficients of these, the number of representations, you can say, by the genus, is equal to a product of some local densities, which are some p-adic integral or p-adic limit. So you take some infinite product of some p-adic limits, and that gives this number that's being averaged here. So this is just an average over the integers here at the top. And Siegel says, actually, you can write it as an infinite product of some local information. So he gave a way to sort of compute this. And it also turns out to be the Eisenstein series component, if you know something about modular forms, of the theta function. And you can see from this definition, if you look at this definition up at the top, you can see that actually it only depends on the genus. So it's a genus invariant. It doesn't depend on the particular form, just the genus. So the Eisenstein series component must be the same for everything in this genus. Any questions so far? Okay. So a number of people studied these numbers, the number of representations by the genus, and we're going to restrict ourselves to the ternary case. So that means 3 variables. And Jones said that if you take the discriminant of Q, which is, I'll describe that a little bit later what that is, but basically it's the determinant of a certain matrix that gives the quadratic form Q. And if the GCD of n and the discriminant is 1, then this actually is a Hurwitz class number, essentially, which is consistent with what we saw in the case of what Gauss looked at before that. His proof was actually bijective. So he really constructed a binary quadratic form from each ternary quadratic form. Or he constructed a certain number of them from the representations of the quadratic form, from the representations from the quadratic form. So then the question remains, what about when the GCD is bigger than 1? So that's what we're going to be interested in this talk. We're going to extend this to be able to take the discriminant having some GCD with n. Well, I gave you one example already, the sum of 3 squares, where we got some class numbers. So let's see how that goes. But we didn't look at the genus, we actually looked at the theta function. But there's something special going on there, because the genus modulo equivalence classes is actually 1 in that case. So when this has just 1 element, this average only has 1 term, and then this cancels, this omega q just cancels, and you just get RQ of n. So the number of representations by the genus is the number of representations by the quadratic form in the special case when the class number is 1. The class number of, that is to say there's only one class of isometries inside the genus. So in the special case when the GCD is 1, Jones says the left-hand side is a class number. So the right-hand side must also be a class number because they're equal. And this explains the formula that Gauss found for the case when the quadratic form is the sum of 3 squares. So now we're going to extend this to consider the case when the GCD is not 1. So let's look at the formula in a slightly different way. Let's recall first of all this class number relation. So so this is Gauss's class number. That's the number of primitive binary quadratic forms. And if you look at the number of primitive binary quadratic forms of d times f squared, it's related to the number of primitive forms of discriminant d up to some factor that is essentially f times some normalization kind of factor here. So this product here. Okay. And if you rewrite it, you actually can combine all of, so remember there were a number of cases. And if you use this relationship, you can actually rewrite the formula in this way, in a uniform sort of way that works for every n. So in particular, in the special case, when n is divisible by 4, h of 4n is equal to 2 of h of n, and you get, the little h's are equal, and you end up reducing down, and that's how you get division by 4. And when it's 7 mod 8, it's actually equal to 2h of n, and then this cancels completely. And we're going to also take, in this case, it doesn't show up, but later on, we're going to use the fact that if this is not an integer, we'll take it to be 0. And we can find other examples from taking all the class number 1 forms, where we take the number of representations by that particular quadratic form. So this is the sum of a square plus 3 times a square. And we get the following formula: 2 times h of 12n plus 4 h of 3n minus 6 h of 4n over 3 minus 12 h of n over 3. And whenever n is not divisible by 3, these will be 0, these two at the end. But what I want you to note is the fact that the parameters that show up here, this 12n, this 3n, this 4n over 3, and this n over 3 are all a square times n over 3, right? So this is 4 times n over 3. This is 36 times n over 3, and this is this is 36, and this one is 9. So 9, 36, and 4. So they're all a square times n over 3, and that means that we're in the same field every time. So this is counting some number of representations, some number of classes in some special way that all have the same, they're all coming from the same field, but they're different orders in the sizes. And probably there's something combinatorial going on here. Maybe you can extend what Jones did to understand this, but we're not going to take that perspective in this talk. We're just going to look to try to get other formulas like this one. And then I'm going to do R115 of n, which is 2h of 20n minus 4h of 5n plus 10h of 4n over 5 minus 20h of n over 5. And again, everything is n over 5 times the square for 25 and 100. Okay. And even the coefficients kind of sort of satisfy some relation, although at the point of when this was constructed, you could kind of see that they're related, but we didn't exactly know how. And we'll hopefully understand that at the end of this talk. Okay, so before I move on to stating the theorem, I want to say a little bit about quadratic lattices and quadratic forms. So a quadratic space is a vector space over Q that's given, it has a built-in quadratic form on the space. So if you take Euclidean space, this would just be the sum of squares, right? Would be the quadratic form that's defined on it, because the distance is the square root of that quadratic form. So that's exactly this case. This is Euclidean space. And then in that vector space, which here the different directions are orthogonal to each other, but they don't have to be. So there could be some cross terms. We can form a lattice by taking some vectors v1 through vl and taking the space, taking the lattice spanned over z from those vectors. And we're going to assume that we have L independent vectors, so that this is, if we take the tensor with Q, we should get the whole space. So my lattices will always be of that type. And there's an associated quadratic form. So if I take the quadratic form, this one, the one defined on V, so this is that Q, and I apply it to a sum, j from 1 to L of xj vj, then that defines a quadratic form where my x's are integers, right? These x's here are going to be integers, and I take multiples of those vectors vj. And then I can also write this using some matrix that I'm going to call BL. I can write this as x transpose BLX. So that BL is going to be this matrix that comes from this, and we're going to use that to define the discriminant in a moment. And there it is. The discriminant is just the determinant of this matrix. So for the sum of squares, it would just be 1. Some people use a half here. I don't have it in this case. And if you had a half, then you'd have 2 to the L as the discriminant instead. So if you look at different authors working on quadratic forms, some of them will have a factor of 2 here and others will not. So there's a little bit of variation. So if you're comparing, you always have to be a little bit careful. Now, we're going to look at special lattices that are called stable lattices. So what is a stable lattice? Well, for an odd prime, we're going to call it p stable, so stable at the prime p, if the order of the prime p dividing the discriminant is at most 1. So in other words, we have some restriction on the prime power dividing this discriminant. And there's a more complicated definition for p equals 2. I won't write it down, but there's some definition. And these are related to something called Watson transformations. So a Watson transformation, it takes a lattice L and it defines another lattice, which are the vectors in L for which it's always true that Q of x plus y is congruent to Q of x modulo m. So we pick an integer m, and we take the ones where this is congruent for every y in the lattice. And then the Watson transformation gives, so this is some lattice that's contained in L, it's smaller than L, and then we scale it. So for instance, it could be that when you take lambda m of L, maybe you get m times L, and then we factor out the m. So we may not have a primitive lattice, we might have something that's everything's multiplied by some factor. It has a GCD in some sense. And then we scale by dividing out by that common factor to make it primitive. And what's important for our purposes is that you can always get a stable lattice by taking finitely many Watson transformations. So these Watson transformations, the lattice lowercase lambda of L will have a discriminant with less powers of the primes dividing M. So for instance, if I just take M to be a prime P, if P squared divides the order, then the power of P will go down. And so we can iteratively reduce the powers of the prime P until this condition is satisfied. So I'm going to give a theorem about stable lattices, but I wanted to say beforehand that somehow this is still not a strong restriction because we can always get there by a finite number of steps. And we'll actually give a statement also that relates what happens when you actually do those steps. Okay, so we're going to try to get one of these class number formulas like Gauss's, the way it was rewritten as a difference of two class numbers. And let's suppose we have a stable lattice, and we're going to take the quadratic form to be the quadratic form coming from that lattice, so Q sub L. And then we have something called the Hasse symbols, which are something that takes values plus or minus 1. In particular, if you know something about lattice theory, we take plus 1 if the localization LP is isotropic. Isotropic means it has an element of norm 0. And anisotropic, we take minus 1. So anisotropic means it does not have an element of norm 0. So the quadratic form defined over the p-adic integers, we check whether the lattice, looking at it tensored over ZP, does it have any elements of that have sort of distance 0 in some sense. And for most primes P, this actually will be true. It will be isotropic. Anisotropic primes are rather rare. There can only be finitely many, and actually it has to be there's an even number. We also define this number EQ to be either 4 or 1, depending on some property at the prime 2. I'm going to ignore that mostly. So basically, just to write down a formula, I define some extra factor here. And I'm going to define this P to be the discriminant times, so this discriminant is the discriminant of the lattice, the same thing, times a 2 power that really just deals with some small issues at the prime 2. Again, I'm trying to gloss over a lot of what's happening at the prime 2 because it's slightly more technical, but for the purposes of understanding the theorem, you shouldn't need to know too much about it. And what we get is the following theorem. If we have a stable lattice, so this is only restricted to the stable case, then the number of representations by the genus is 12 times the product of the primes dividing this. So the reason that we needed to divide out this is that sometimes we want to get rid of the prime 2 showing up there. So this might be 2 to the minus 1. If the order of the prime 2 is exactly 1, then this will be 1 over 2, which will exactly cancel there. So we may or may not have the prime 2 in here, even if it divides the discriminant. And then we take the prime P plus this Hasse symbol, and we take 1 over that. So we take 1 over this product, so it's sort of a normalization factor in front, 12 divided by this product. And then we take the sum of all the divisors of this math frac P. We take the product of all the Hasse symbols of the primes dividing F times F itself, and then we get the class number of EQ was this number that's either 1 or 4, DQ was the discriminant, times N divided by F squared. Okay. So this will give exactly the kind of formula that we saw before. So you'll note that the EQ, DQ, N, if we take Q adjoin square root of minus this number here, if we take Q adjoin square root of minus this number, we get a field. And since we're always dividing by F squared, we'll have the same field every time that we're taking the class numbers from. So this will give exactly that the parameters inside the Hurwitz class number always differ by a square, which means if you look at it from the point of view of fields, I know I've been talking about discriminants of quadratic forms, of binary quadratic forms when I talked about the class numbers, but there's also a relation with quadratic orders in imaginary quadratic fields, we're always looking at the same field here. Okay, any questions so far? So let's look at an example which we saw before. So this was one of the ones that I had found with Cutchin-Brinkman. We had this, the square plus the square plus 3 times the square. This quadratic form, we had gotten a formula before, but let's try to get that formula because this is a stable lattice. It's a quadratic form for a stable lattice. So the discriminant is 3. This math frac P is 6, and the EQ happens to be 4. If you do a calculation, you can compute all of the Hasse symbols. So the Hasse symbol at the prime 3 is -1. The Hasse symbol at the prime 2 is 1. And if we put that together, we have 12 divided by 3 minus 1 times 2 plus 1. So we take the prime plus the Hasse symbol. So 3 minus 1, 2 plus 1. So 12 divided by 6 is 2 times h of, and then we get EQ times DQ is 12. So we should have 12 times n divided by f squared, where we sum over all the f's. And f here is 1, so we get a 1 in front. F here is 2, so we get a 2 in front, because we're dividing by 2 squared, right? And then do we have a plus or minus 1? If you look at the formula, we should take the product of these Hasse symbols to determine if it's plus or minus 1. And we're taking the product over all primes dividing f. F is going to be, in this case, 2. So we just take this one Hasse symbol here. We have a 1 there, so that's why we have a plus. Now, for the next term, we're going to divide by 9 and take 12n divided by 9. So that's why we get 4n over 3. So then f is 3, because it's the square. We divide by the square of f. So that's why we have the 3 here. And then we have the minus because the S3 star of L is -1. So that's why we have a minus sign. And then this one is exactly taking f is 6. So we take the product of these two is also -1, and that's why we get a -1 there. And that gives exactly the formula that we had before. So now these numbers in front suddenly have a meaning, and they're coming from a clear place, and we understand where they're coming from. And we also even understand why we have plus or minus in each term. Questions about that? So the formula with Cutchin-Brinkman was originally found using modular forms. We proved it using what's called the valence formula. Essentially, you check the identity for enough choices of n, and then you can conclude it must be true for all n. But here we sort of have an explanation in some sense for the formula, as opposed to it just happening to match. Okay, so now you might ask, what happens with non-stable lattices? Jones doesn't have this restriction with stable lattices, so seemingly something must be similar there. So in this case, we're going to use the fact that the Watson transformations will reduce us from a non-stable lattice to a stable lattice after finitely many steps. And then what we'll do is we will relate the formulas before and after taking the Watson transformations to get these kind of class number formulas. And this will give us an algorithm for formulas for non-stable lattices, but it won't be a formula I'll just write down in one step. It's not as straightforward as the stable lattice case. It's going to be some linear combination of those. Okay, so how do we go about proving these theorems? Well, we start out with these local densities that Siegel had defined, which can be written, as I said, as a p-adic limit. So we take the limit as r goes to infinity of the number of solutions modulo p to the r of x transpose BL x equals n, this actually should be, this is just a vector. I wrote it here as a matrix, but it's just a vector, X transpose BLX. So there's a more general definition where you have L comma something else, but the number we're representing is n, that's one dimensional, so that's why it's one dimensional here. So it's coming from an L dimensional space to a one dimensional space. And so we're just counting the congruences of the number of solutions congruent to n modulo p to the r. So this is the number of solutions modulo p to the r in some sense. And then we divide by some power of the prime p, and we take the limit, and lo and behold, Siegel showed that this limit, actually, if you take the terms, after finitely many steps, he shows that it's a constant. So therefore, the limit exists, and he calls that the local density. He even gets a bound on how many steps you have to take before it becomes constant. And you get this rather explicit formula. If you take the number of representations by the genus, this is exactly pi to the L over 2 gamma of divided by gamma of L over 2 times the discriminant to the minus 1/2 power times n to the dimension over 2 minus 1 times the product over all primes of these local densities. So this is a rather explicit formula if we can compute these local densities. So now let's suppose we have a stable lattice, and the good news here is because it's stable, the local densities are easier to compute because the p-adic orders are restricted. So this eta p is just the order of the prime dividing n, which is unrestricted, but the order of the prime dividing the discriminant is always going to be 0 or 1. If the order is 0, then we get two formulas. One of them is when 2 divides this. So this is when the order is even. So the power of the prime p dividing n is even. Then we get this formula, 1 plus 1 over p minus 1 over p to the new p plus 2 over 2 plus this Legendre symbol divided by p to the new p plus 2 over 2. And in the case when this is odd, we get an even simpler formula of this type. When the order of the prime dividing the discriminant is 1, then we get two cases again. And in both cases, we have this Legendre symbol showing up, but in a slightly different way. So this MP is kind of a lattice that's what we call splits off from L in a certain way. I won't go into detail about what this is, but there's L can be written in terms of M. LP can be written in terms of MP rather. And so this discriminant is showing up there, and then we can get this Legendre symbol. Yeah. Okay. So these are our Legendre symbols, these fractions. But the point is, because we restricted the order of the prime dividing DL, we're able to explicitly compute this. There are formulas in the general case, but they're rather large and clunky and hard to deal with. My advisor, Tonghai Yang, has a paper in the Journal of Number Theory where he writes down a formula for all cases, but it has it depends on a bunch of parameters, and it's a little bit hard to use in general. So by restricting to these two cases, we're able to get something very explicit. Okay. So in the case when the prime does not divide to DLN, so that would mean that if P does not divide the discriminant, and it also does not divide N, and it's not 2, then we're in this first case, and nu sub P is 0. If nu sub P is 0, then we have 1 plus 1 over P minus 1 over P, so those cancel, plus, and then we have minus N DL over P divided by P. So 1 plus the Legendre symbol times 1 over P. And this is exactly the Legendre symbol for the field, essentially. The field Q adjoin square root of minus N DL, which is exactly what's showing up in our formulas. So this is sort of natural in some sense. Okay. We're going to relate this to an L function. So for a character chi, we have an L function, which is just the sum of chi of n over n to the s, which can be written as an infinite product of 1 over 1 minus chi of p to the minus s. And if we take the character chi sub d to be d over n, then our product of the local densities is 1 minus p to the minus 2 over exactly the factors that show up here for s equals 1. So somehow, if we fill in the remaining primes, the ones dividing n times dl, we would have the L function showing up for chi minus n dl at 1. And there'll be finally many other factors that come from the primes dividing n dl. There's also a zeta of 2 in the denominator showing up, but that's something we can compute explicitly. And remember, there were some factors with powers of pi, and so that's exactly going to be what's canceling here. I mentioned this earlier on, but let me mention it again. We have Dirichlet's class number formula, which relates this L value to the class numbers. So this is where the class numbers enter the picture. And if we have a fundamental discriminant, we have this relation, but also the Hurwitz class number and the regular class number are equal, other than a normalization factor that could be dividing by 2 or 3 if we have the discriminant is -3 or -4. So I left that out. They're basically equal, but there's a factor of 2 or 3 that's different sometimes. Okay. So h of d divided by omega of d is exactly capital H of d. I should have divided by the omega of d there. So what we want to do is we take the other factors from the primes not dividing n times that are dividing n times the discriminant. We'll have finitely many factors, and we're going to relate those to get some relation between the class numbers. So basically, we'll add and subtract some numbers that relate the other class numbers, but for the same field. So that's why we're going to get these squares showing up. And we're going to compare what happens when we change the number n by a square, having something to do with these primes, and how does that change the formula with the class numbers, and how does it change the formula for the number of representations? And we're going to show that they match in some nice way. So we're going to use this class number formula, which I mentioned earlier, and then the Hurwitz class numbers can be written as a sum of these class numbers, which also was written down earlier. And that gives us a relationship between the class number h of n, the Hurwitz class number, and then when I divide by a prime to some even power, I can get a formula relating it. So I get a nice relationship between h of n and h of n divided by a large power of the prime q, everything I can take out, essentially, the highest even power that I can divide out, and I get a relationship. And this allows us to relate the formulas for the representations and the ratios of those with the ratios of the class numbers. So that leads to this proposition. Suppose we have a ternary lattice, doesn't have to be stable, and Q is a prime for which this GCD is 1. So Q does not divide 2dl. Then the number of representations by the genus of n times Q squared divided by the number of representations of n, sorry, there's an extra parenthesis here, is the same as the ratio of these class numbers. So if I can show the claim for n that this is related to that class number, then I get the same ratio here. So basically, this allows me to assume that the power of Q is at most 1, because I can use a kind of inductive argument to get the claim that I want when I add in the Q squared. Does that make sense? So I'm going to use this inductively in the end. And basically the point is, if I compute the local densities for the genus with nq squared and the genus with n, then for every prime other than q, the local density is the same. So all the factors over here will, on the left, will be the same, except for some factor that changes, and I just have to make it match exactly what's here on the right-hand side. So we can compute those local densities that we had in a previous slide. We can compute those, say, for instance, for the stable lattices, we can compute them explicitly and show that the ratios match. And then we do the same thing when we take a prime that divides the discriminant, but to order exactly 1. So if we're taking stable lattices, then either the prime does not divide DL, or it divides it to order 1. So these are the only cases. Now, for non-stable lattices, it could divide it to a higher power. So we may not be able to use this proposition. But when we can use it, when it divides it to exactly power 1, we get a relationship between the number of representations by the genus of np squared and the number of representations of n. And what we get is a sum of 2 class numbers. And the nice thing is we can do this for any f, because things cancel out in the numerator and denominator. We can divide by any power, by any square f, which is going to be useful for the induction that I was indicating before. So this ratio will be always the same as this ratio. And again, basically the idea is if I can show it without the power of p squared there, then I can show it with the power of p squared by using this identity. That allows me to replace everything in the sum. If I look at the theorem statement, it's going to allow me to replace everything in the sum with the thing divided by f squared. I replace n with n times p squared. And if I replace this with n times p squared, we see that everything is exactly matching. So the ratio is exactly what we need it to be. And again, there's similar identities for the prime too, but I'm not going to write those down. And now, once we have all this, we're ready to do some kind of reduction argument. For the square part of n, we use the previous propositions, and that reduces to the square-free case, which is the base case, essentially, of the induction. And then for the square-free case, we use the Dirichlet class number formula to get exactly the class number that we're looking for, and now we're done with the stable case. I'll try to say something quickly. I think I'm running just a few more minutes left time. So let me just quickly say what happens for non-stable lattices. So for non-stable lattices, you can relate the number of representations by the genus with the number of representations by the genus for some other number, which might either be n or n over p, and also the number of representations for the genus of some simpler lattice k. And after enough steps, everything is stable because we know after finally many steps we reduce to a stable lattice. So each time the powers of the prime p dividing the discriminant go down until we get a stable lattice. And then eventually we can plug in the stable lattice formula that we had before. And this will give us an algorithm to construct formulas. There's an alternative approach, which is to use this theorem, which essentially we can use the propositions from before. Whenever the power of the prime p is dividing the discriminant is at most 1, we can use this relationship. And then there's finitely many other primes we still have to we have to compute the local density essentially. And I'm going to try to, in 1 minute, give you what happens in the case of the 1,175. This is stable at every prime other than 5. The GCD, if the GCD of n and 5 is 1, then the previous page gives us this relationship where we have everything except for C5 of NL, which is this local density. And then we just need to compute the local density, which can be done. And we get either 1 or 2/3, and that gives us a relationship. And even in the case when it's divisible by 5, we use this reduction with Watson transformations, and we get two other lattices, one that's from the Watson transformation and one that's simpler in some way. And then it turns out in this special case that these are both stable. And then we plug in the formula for the stable lattices for these two cases, and that gives us this formula. And you can combine all the formulas in this case because these extra terms that were added in are all 0 if n is not divisible by 5, and then that gives us everything we want. Okay, so that's it. I hope you found it interesting. If there's any questions, I'm glad to answer them. Thanks a lot for your time.
Okay, thank you, Ben. We have time for maybe a quick question. Anyone in the room has a question for Ben? Okay, no questions from the room. Anybody online have any questions for Ben? Just unmute and speak up. Yeah. Okay. No questions. Let's thank Ben again.
Thanks, everyone.
Yeah, thanks a lot, Ben, for really finding time, on all this,